Hi everyone, welcome to the lecture 2 of module 2. In the previous lecture, we started with our first linear ordered data structure, which was the list ADT. We also saw the different instantiations of this list ADT in C++ specifically, as well as the various operations and implementations that are possible for the list ADT. Today, we are going to discuss two other linear ordered data structures, which is stacks and queues. So the agenda for today's lecture include we are going to cover stacks, including the what's the ADT behind stacks, as well as the operations that are supported by the stack ADT. We'll be discussing the conceptual model, how do stack ADTs work. Finally, we are also going to see the ways to implement the C++ implementation and the use cases of where stacks are commonly used. We are going to do the same in the second video, which will be focusing on queues, which is what is the ADT behind queues, the conceptual model, as well as implementations. Also, we are going to compare the performance of these various implementations, as well as we are going to discuss the use cases. So let's get started with stacks. So you guys have already seen stacks in normal life, which is you might have uh, metaphorically seen this in a stack of pancakes. Or let's say if you are trying to keep books on top of each other, you are basically seeing a stack of books. Or another example could be if you ever go to a buffet to have some food, you might have seen the plates are stacked on top of another. So that's another metaphor for stacks. So stack is kind of like seen everywhere around us. And the stack ADT basically follows this principle of last in, first out, which is, let's say if I'm trying to keep plates on top of each other, we know that we are going to pick up the topmost plate, not the bottommost one, which is like whatever is most recent is picked up first. So that's a big distinction between the stack and queue data structure. We are going to discuss queues in the next video, but how stacks work is whatever came last gets out first. So that's one important thing that you need to focus on. In this particular slide, you can see in the center there's this toy which you might have already seen in programming fundamentals 2. This is a common problem of stacks which is called the Tower of Hanoi problem. And in this problem, we basically have three pegs and a number of disks. The disks are ordered such that the smallest disk is on the top, and the largest disk is on the bottom, and the disks are increasing in an ascending order. So this problem is also solved by stacks. We are going to see that in the later half of the course, but right now, um, like this is another example or use case of where stacks is commonly used. The problem basically demands you to move all the disks from one peg to another with some certain rules that you cannot have a larger disk on top of a smaller disk, and there are other rules as well. We are not going to discuss that, but we are going to discuss the stack ADT, like what kind of data and operations does it support. So stack usually consists of a set of items as well as how many number of items does it store. So whenever you are trying to design a stack data structure, whether it's an array based or a linked list based that we are going to see very soon, you need to keep a track of how many items does the stack store. The third data that is a part of the stack ADT is the top pointer, which is what what is the element on the top of the stack. The operations that are supported by the stack include push operation, which is basically allowing you to insert an element on stack. Pop allows you to remove and return the last inserted element. In some cases, it just removes the element, it doesn't return, so it depends on the implementation. Peek allows you to uh, see what's the last inserted element and it does not remove it. Size returns the number of elements. Like again, this size operation is specific to some languages, and other languages it's not supported. But these three and the is empty one is like a common stack ADT operations. Those four definitely come under common stack ADT operations. The fourth one is empty, which checks whether there are any elements in the stack or not. So let's discuss how we can implement stack. So the way stack works is I'll first give you some conceptual ideas, which is usually we store stack in the form of this rectangle. Right now it's empty. So let's say if I do a push operation, which is push 5, it's going to insert this number 5 in the stack. Now, if I do another push, 6, it's going to insert it on top of this. Also, I forgot about that, like there'll be a top pointer pointing to the topmost element. Initially, when the stack is empty, top is usually set to -1 because we know that there are no elements in the stack. So right now there are like 0, 1, 2, 3, 4 up to like n elements in the stack or n-1 elements. The top is pointing to 6. Now if we do like pop operation, this is going to remove this 6. So I'm going to remove this, and now the top starts pointing to 5. So let's delete this. Now if I do again a pop operation, it's now going to remove this 5. So basically this is removed. Top now becomes -1. And finally, if now we do an operation like empty or is empty, it could be any one of them, this should return true because our stack is empty. Now let's discuss how we can implement this in the form of an array. So I'm going to remove all the operations from here. So how we can do that is we can have a class called, let's call it stack array. Now this class has a few data members. So since we are trying to encapsulate the inner level details of what this is going to store, what we can do is we can store this in the form of an array of size, some size which is defined or given to you like a maximum size. Also, since we have this top pointer that we need to maintain, we need another variable. So I'm writing this in the form of like for a stack of integers, but let's say if you want to do it for generics, you can just do like template and follow the convention, which you have already done in the first C++ refresher. Next, if we talk about the public operations or methods that's supported by this data structure, it could have the push operation, which is basically a method. It won't return anything, but it will take in some item which is int x. There could be a pop operation, which is it's going to return some value. There's going to be a boolean empty, which is going to check whether our stack is empty. And the last one was this peak operation, which is just going to return what's the topmost element. Now, you can also define a size variable. Like some people do that, some people don't do that. So if you want, you can keep a track of the size by using an additional size variable. And whenever you are trying to push an element in this stack, you're going to increment the size and so on. Or whenever you are going to pop an element, you're going to decrement the size and so on. So I'm not going to discuss like each of the functions because we have like limited time and we have to do all the data structures together. But I'm going to just discuss like one of the functions for the sake of time. So let's say if we are trying to implement the push operation, how we can do that is Like if we have a void push int x, again, like I'm leaving this out, but this has to be something like stack array followed with the scope resolution operator, because we are defining these outside of the class. So how this works is, for the sake of simplicity, I'm assuming that I'm not assuming that there's not going to be something tricky here, but like simply if we talk about, you're going to just do ARR of plus plus top is equal to x. So what it will do is, like initially top is -1. Let's say the stack is empty. So if the stack is empty, it will basically insert the number. Like let's say if we call push 5, this is going to insert 5 in our array, because now right now the array is empty. I can draw it in the form of array. So basically we have this array that's defined from 0 up till size, which is the bigger size. So this bigger size, or let's call it max size if you want. So this is the maximum size, and this size is different. It's the, like how much is the number of elements in the stack, while this max size, some people call this capacity, is the maximum capacity. So like whenever we are implementing an array, we need to have a finite size. That's why we have this max size variable. So when the stack was empty, if we try to call push 5, now top will be incremented from -1 to 0. So we are on this position, and there we are going to add 5. And let's say if we do another push 6, now the top's value is already incremented, because earlier it was -1, then it became 0 at this case. So if we do like push 6, it's going to insert 6 and so on. Again, I'm like just simplifying you this. There's a question on Stepic, as well as we have provided you the solution on how to implement the stack. Look into that. It's like pretty straightforward and easy, so I'm not going to cover that a lot in depth. Similarly, when we talk about pop, it will just be like ARR of top minus minus, like you're going to return that value, which is ARR of top minus minus, and so on. In case of peak, you're just going to return like ARR of top. And finally, when you're implementing, like you also might need to implement some checks, which is, let's say if the array is empty, and if you do a pop operation, or if the array is full, like I omitted that here, which is if the array is full, you might have to check whether the top is less than or equal to, um, is less than the maximum size of the array, and so on. Like otherwise, you might just want to throw an exception stating that stack is already full. So let's discuss the characteristics of this implementation, which is, now this implementation has a fixed size, as we saw. It stores similar elements, and we can access these elements through the top index. When we talk about the operations, it supported the push, pop, peak, size, and is empty operation. I didn't define the size one, but if you want, it's like pretty straightforward. It's not too difficult, so I'm going to skip that. Now let's talk about the performance. So whenever we were pushing an element, we wrote just one line of code, which was this ARR plus top is equal to X. So we are adding numbers in the front of the array, or in the back of, like at the last index of the array, which is also the address of the top pointer, or in this case, the top index. So it's a it will just take like constant amount of time to push an element. Similarly, for pop, we would just do something like ARR of top minus minus, like we are going to return this value. So there's going to be just one statement. Again, it will be O of 1. For peak, it would be just like return A of top. So it will be again O of 1. And size would be again O of 1, because we are already storing the size variable. if we were not storing the size variable, then we would have to do something like arr.length, or you have to go through the entire stack, and that would be O of n. So again, there's this trade-off between like storing size as an additional variable versus trading it for performance. So it really depends on what you're trying to achieve. And the last one is empty. So that's going to return just this equation that top is not equal to -1, or it's going to return top is equal to -1. So it will return true in that case. And then I'm going to just like erase this. So it's like top is equal to -1, because if that's true, that means our stack is empty. Otherwise, it's not going to return, like it's going to return false. So again, all the operations in the stack ADT, in this case, when we are implementing it in an array, can be achieved in O of 1. So what are the benefits of this? So one of the clear benefits is like it's very fast for the purpose it's used for. Like let's say if we have a scenario where we want to retrieve the element which we pushed in the end, or we are trying to have a scenario like stack, it's going to be very fast because all of the operations supported are in O of 1 or constant time. The drawback of this approach, like implementing specifically as an array, is that it has fixed size. So it's like constant time and fixed size, as well as no random access. Now I want to emphasize on this part, the no random access part. I see a lot of students do something like this, which is S of I, where S is the stack. Like this is absolutely not allowed, and it's like forbidden throughout the course. If you try to do something like this on a stack, linked list, or a queue data structure, that's not allowed, because you cannot go at any place in the stack. Even though it's array based, the interface only supports you to call the the implementation actually only supports the 5 operations. Like let me go back a little bit. So here we saw that the although we have this array, all of this is encapsulated within the stack array class. So we don't know behind the scenes it has an array or not. Like if a programmer is trying to call this interface by creating a stack array object, they cannot manipulate like ARR, because if you try to do something like uh, S of I, it would just say like you're trying to access private variables, which we don't want to expose to other people. So again, like random access is not possible. In the next video, we are going to see how we can implement using the stack using linked list, and we are going to compare the performance of the two approaches.